Okay. All right. So we're going to begin with the first chapter, the introduction. Um, as you're well aware, I'm hoping everybody's well aware that this is a sequence of three classes, 115, 215, and 315, right? It's called as Electrical and Electronics Engineering. Just to give you a little bit of a history, E major students take three circuit analysis classes, okay? And that runs for one entire academic year. If it's split into semesters, it would be two courses. Cal Poly is still on quarters, so it's three. So EE students will take 113, 211, and 212. That's for one entire academic year. Then they take the electronic sequence of classes where they learn about semiconductors and devices. And so that, again, runs for one entire academic year. No matter where you go in the world, this is pretty standard. When I was a student more than 35 years ago, I did the exact same sequence. I learned the exact same fundamentals, right? Most of the fundamentals, they are not going to change, right? My son is in elementary school. He is learning the alphabet. He is learning the words, the spelling, math, everything's still the same, right? The, the mode of instruction, the techniques of instruction might change. The homework would change, but the fundamentals don't change. So E students take those classes. CPE majors used to take those three circuit classes and would take the first two of the electronic sequence, meaning they would take 5 quarters worth of circuits and electronics classes. Okay. You all are taking the 115, 215, 315 sequence. So instead of 5 quarters, you get done within the first, you get done with 3 quarters. So you get done within one entire academic year. Okay. So this class, otherwise, until a few years ago, you would have been taking this with EE students, right? This was specifically designed by Dr. Protonov, who is now the chair of the EE department. He designed this entire sequence along with the labs. So that's a tremendous amount of work actually that he put into designing these. So all of the slides and everything that we use for these classes are designed by him. They are approved by the curriculum committee of both the E and the CPA departments. And then the instructors who are going to teach it, we have to like follow that sequence. There'll be some minor changes here and there, but for the most part, we are required to follow what has been approved by the departments. Okay. So you are again learning about electric circuit analysis as well as semiconductor devices all in 3 quarters, right? So it's a little bit compressed in that way, but as a CPE student, this is actually, this required material. So if you're thinking that, I'd mostly be interested in coding, not interested in hardware that much, well, this is kind of required and essential. So if you recall, I talked about career pathways where you can go work as an embedded systems engineer, where you would be required to have hardware as well as software knowledge, right? All right, so let's begin with the basics. So I already have my slides uploaded in the class notebook. All students have been added to the class notebook. So if you open up your SharePoint or OneDrive, you should be able to see that OneNote file in there. And the OneNote file, the title is EE115. So when you open it up, you should be able to access my annotations directly. All right. So introduction to EE. Now, this talks specifically about EE, but I think it goes for any branch of engineering that we do require certain math skills and certain math knowledge, right? So what are the skills that we want in EE? Well, electrical engineering is concerned with a lot of dependencies. One quantity depends on another. Or if you have like a circuit, electrical circuit is basically a graphic illustration of a real life system. And so each component is dependent on something else. So EE is primarily concerned with dependencies. So we use a lot of mathematical functions, right? So right here, we depend on a lot of functions. Actually, let me change the color of the pen. And then, of course, the operations on the functions and operations with those functions, okay? So what do we mean by dependency? And what do we mean by operations or functions? Well, dependencies. Let's start with the example of a electrical system. We have these systems in front of us, right? You have your mobile phones, you have your tablets, you have your laptops. We have this projector system, this monitor here. All of this is an electrical system, right? If I draw a graphical illustration of the system, we call that a circuit schematic or an electric circuit. Okay, so in that electric circuit, we have some sources and we have some loads. So in any electrical system, we have a source. That source is supplying energy. And then we have loads, LOAD loads, that are receiving the energy. Now, everybody's familiar with the law of conservation of energy, right? Standard energy is neither created nor destroyed. It is always converted from one form to another. So with regards to an electrical circuit, we have a source that is supplying electrical energy. Depending on the loads could be resistors, capacitors, inductors, diodes, transistors, it doesn't really matter. They're all receiving the energy. Okay. So when they receive the energy, some of the energy is lost in the conversion process. Okay. The loss, of course, the loss of an energy inside a system determines how efficient or describes how efficient the system is. So let's say if we take an example of a simple circuit with a source and a resistor in there, well, the source is supplying electrical energy. The resistor's job is to resist or oppose the flow of electric current. And so when energy is transferred to the resistor dissipates the energy as heat. So it dissipates thermal energy. So some portion of the electrical energy is converted into thermal energy and is dissipated as heat. And that is what we mean by dependencies. Okay, so we're converting one physical quantity to another. We have resistors where electrical energy is converted into heat. We have solar cells where light is converted into electrical energy. We have LEDs and other kinds of light emitting diodes that convert electrical energy into light. Right, so there's energy conversion that is taking place that is dependent on the output of which is dependent on the input. And then the functions that we use to describe these could be summation, inversion, integration, differentiation. When we get to capacitors, inductors, we use differential equations to solve for those, for their values. Okay, so there's a lot of math involved. There's a lot of math involved in any system of engineering. All right, so let's take a pause. Think over it. Let me know if you have any questions. That basic introduction. Okay. All right. So some aspects of electrical engineering. We deal with systems that implement complex functions. Right? That is, again, true of pretty much any engineering field, whether it's mechanical engineering, civil, industrial. That is kind of true or a factual statement about all fields. The individual systems or electrical systems are made out of individual components. In 115, we typically learn about two terminal components, such as resistors, capacitors, inductors, which I believe you have studied in the physics classes. You may have studied it, or you may be studying it right now, or you may be studying it in the future. But for the most part, I believe there are some prereqs that you have already covered in your first year, where you learn about resistive circuit analysis, KVL, KCL, Ohm's law. Am I mistaken? Or have you covered all of that? Yes, no, covered it. Okay. Some nods, some shakes. Okay. All right. So systems are made of components. Those components, again, typically are resistors, capacitors, inductors. Those are passive components. And then we have our nonlinear devices, which are diodes, transistors, bipolar junction transistors, field effect transistors. Those are some things that you'll learn in 215 and 315. Okay. And so components could be resistors, inductors, capacitors, diodes, etc. Okay. Now, when you have a simple system, you have a source and you have a load. We call that described a circuit. As the circuit grows with the number of components, with more and more sources, more and more loads going in there, it gets a little bit more complex. We might use a different term to describe it. We might call it like a network. Okay. Oftentimes, the words network and circuit is kind of interchanged. So they are sometimes used as synonyms of each other. So you might say this is an electrical network. You might say this is an electrical circuit. For the most part, I will always use the word circuit. I would rarely ever use the word network. Okay. So when we are working with smaller circuits or small systems, we typically just use the word circuit. So electric circuit. In the name of these courses or classes are typically just electric circuit analysis. When I went to grad school, the same class that is called circuit analysis here was called as network analysis. It was pretty much the same class. There's no difference. Okay, and as I was saying, if we use graphic description to illustrate the connection of the system, that is a schematic, that circuit schematic on paper, on screens now. So 2D representation is known as the circuit diagram. Okay, so we have circuit schematics that describe the system, and that is referred to as the circuit diagram. As a simple example, let's take a flashlight. What are the three major components of a flashlight electrical system? We'd have the light bulb, we'd have an energy source, and we'd need a means to control that energy source or the connection between the energy source and that light bulb, right? So if I was to graphically describe it or draw it out, then I would need three things. I would need a source, the load, and I would need a switch. And so if I was to draw a circuit diagram for that flashlight, it would look something like this. And of course, we'll look at all of these individually later on. But I have a source. That source is represented by a either a voltage or a current source. In real life, would be a battery, right? You'd have a couple of batteries. So I'm just going to write battery. And then just for old time's sake, I'm going to draw a light bulb. Which of course nowadays everything's replaced with an LED. That's a filament light bulb. And then the connection is controlled by a switch. That is the representation of an electrical switch. Okay, this is again something that you will encounter going forward into, especially in 215. Okay. And this schematic illustrates the actual electrical connection inside any flashlight. Any flashlight you want to take. Even the small ones that you have nowadays on like larger battery packs. So if you have taken like a portable battery charger, right? Like just on the go, your phone's running out of battery, you want to connect it to a portable battery charger. Some of those have an LED light bulb in there. That schematic is still exactly the same as this one. Very little difference. Okay, there's a switch on there, there's a battery pack, and there's a LED. Press a button a couple of times, it turns on. Press a couple more times, it turns off. So this schematic is known as a circuit diagram. Okay, so it's a graphical representation of an actual system. So far, so good. Okay. So the title of these courses, these three courses that you're taking, 115, 215, 315, it's electrical and electronics, right? So the way it's described, it's electric circuit analysis and semiconductors, which is where electronics come into the picture. And so electrical and electronics, and you're combining and learning about both kind of at the same time. So it's a little bit unique in that sense, okay? As he states here, there is no kind of marked difference between electrical and electronics nowadays. In fact, in India, where I'm from, when we talk about electrical engineering, here in the US or North America, we are typically referring to like electronics engineer. So instead of being an electrical engineer, as I am here right now, I'll be referred to as an electronics engineer back home. Well, back home is in India. Okay. And if we use the term electrical engineer, they are referring to somebody who works with power systems. Okay. There's a little different. But again, not to confuse you too much, this is just a little bit of, little example of how different, same things could mean differently in different parts of and the world. All right, so there is no clear demarcation or delineation between electrical and electronics. But here's the thing. Remember, I said earlier, E students take the circuit analysis classes, and then they take these electronics classes, like so 3 and 3 each. So what E students would learn in the electric circuit classes, circuit analysis classes, would be resistive circuit analysis, capacitors, and inductors. And that's it. No other devices. And then electronic devices would refer to semiconductors or semiconductor devices, which would be your diodes, your transistors, BJTs, and FETs. Okay. So in this course, in 115, you're learning not only resistors, capacitors, and inductors, we are also learning a little bit about diodes. If you have already purchased your lab kits for 145, I think there are some diodes in there. Do you have a parts list or something from IEEE? Or if you open up the parts kit, there should be some diodes in there, I believe. Okay, all right. So functions, what kind of functions are we talking about? Well, functions could be constant, meaning the value of that quantity or that function doesn't change with respect to time. There's proportional, there's linear, right? We have linear relationships, we have constant, we have proportional, exponential. There's a lot of other different kind of functions, but we are primarily concerned with constants. That's where DC circuit analysis comes into the picture. Okay, and then linear relationship, you already studied that in Ohm's law, right? V equals IR. And then, of course, there are some others that cannot be described. Okay. So we studied Ohm's law. Ohm's law was named. Anyone know who is it named after? Named after George Ohm. It did some research in the relationship of the voltage and current as pertains to a resistor. Came up with this equation. V equals IR. Simply stated, he says when current passes through a resistor, it causes a voltage drop, and the voltage drop is directly proportional and is equal to the product of the current and the resistor. Voltage is equal to current times the resistor, mathematically speaking. Okay, so when current I passes through a resistor, it causes a voltage drop, and the voltage drop is directly proportional to the current, and is equal to the product of the current and the resistance. The constant of proportionality is the resistor value. Okay, V is directly proportional to I. If V increases, I increases. If I increases, V increases. So the other way to describe this is, if you apply a voltage across a resistor, current I would appear to flow through that resistor. This is a very important law and the most fundamental of all equations in physics and in electrical engineering. Circuit analysis only requires knowledge of three. All of electrical engineering is built on three. You have Ohm's law, you have KVL, you have KCL. If you know these three and you can apply them quickly and efficiently and correctly, you can derive anything else. And these three are the only things that you need to know for circuit analysis. Any system, whether small or large, can be solved with these three equations. That's it. All other techniques are derived from these three. You have node voltage analysis, mesh current analysis, superposition, voltage division, current division. Everything is derived from these three laws: Ohm's law, KVL, KCL. Master these three and you're good. All right, let's take a pause. Let me know if you have any questions. Let me see, did I start recording or not? It should have, yeah. I did start the recording, but I forgot to switch. All right, I'm switching now. All right, yes. Oh, question being asked is, what is this, right? Is that what you're asking? Oh, on my writing. Oh, this one. Yeah, that's proportional. I. So voltage is directly proportional to I. Because resistance doesn't change in value, theoretically. I mean, it changes with respect to temperature and pressure, and it's affected, of course. But theoretically speaking, let's say at room temperature, the value of a resistor doesn't change. So if a resistor is 10 ohms, at 8 o'clock in the morning, it's going to be 10 ohms. 8 o'clock at night, also it's going to be 10 ohms, right? So it's going to remain constant. But if either voltage or current changes, then the other quantity changes correspondingly. And so its voltage is proportional to current. Okay. Constant. Okay. Constant. In this case, we have voltage as a function of current. Both are mingled, right? You cannot have one without the other. In a circuit, for current to flow through, voltage must be present. If you have a voltage in there, current would be present. Okay. There are some exceptions, unless, I mean, there are exceptions in the sense that if it's an open circuit, voltage could still be present without current being present, right? Prime example are your power outlets. You have power outlets all around you in the classroom. There are power outlets on the lab benches and behind you. It's on the wall right here, on the sides of the walls. All of those power outlets are live. Voltage is present in these power outlets, but no current is flowing through because nothing is plugged in. As soon as you plug in something into the power outlet, that load starts pulling energy from the power outlet. Your circuit loop is complete and current starts to flow. So current needs a pathway to flow through. It cannot flow without a pathway. So I made the statement earlier that the two cannot exist without the other, right? If you have voltage, you have current. If you have current, you have voltage. Unless, of course, it's an open circuit like a power outlet. Then you have voltage that is present, because if you measure it, you'll see voltage present. If you try to measure any current, there's no current flowing through because there's no circuit connected to it. All right, so let's talk about what voltage source is. So here we have a symbol of a source. You will see that many of these symbols are using or use circles. right? So when you have a circle and you have a plus and a minus sign inside the circle, it notes that it's a voltage source. It is a source that is supplying voltage. Okay. So it's a voltage source. And a voltage source has two terminals, one positive, one negative. Okay. So it's a voltage source. And then I'll explain the difference between a voltage and a current source. A current source, as shown here, again, it's a circle with an arrow inside it. Again, two terminals. We call it a current source. Now, in real life, a voltage source and a current source are the exact same box. It's the exact same device. So if you look behind you on the lab benches, you should see there are, let's see, which one is the voltage source? It is, I think that one's the oscilloscope on the top. One is a multimeter, and one is a triple channel DC power supply. Can't see which one from here. My eyes are not that good. It's one of the three dark gray or almost black boxes. Okay, the one on the far right at the top with the biggest screen, that's the oscilloscope in beige. The one on the far right on the lower level is a source and meter. And the other two are either digital multimeters, function generator, and there's a DC power supply. So that's a source. Now that source can function both as a voltage source as well as a current source. Is the exact same box, is the exact same device. There is no difference whatsoever. Then why do we make an exception and draw a different symbol right there? So I'll explain. The definition of a source is a device that is going to supply its rated quantity irrespective of what is connected at its terminals. Again, a source, whether it's a voltage or a current source, is going to supply its rated quantity irrespective of what is connected at its terminals. So if you have a 10-volt voltage source, it is going to supply 10 volts at its output terminals, no matter what you connect at its terminals. This is theoretical, hypothetical, right? In real life, of course, we have power limits. Okay? In real life, we have power limits. So if you say I have a 1,000-volt source, I can put it down on paper. I can't put it down on a lab bench. I don't have a 1,000-volt source, right? So a 10-volt voltage source will supply 10 volts no matter what is connected at its output. It will change the current to match the requirements of the load, but it will keep the voltage constant. Okay, so the voltage will remain at 10 volts. The current will change depending on what the load requires. I will explain with an example in just a minute. And the same thing for a current source. A current source will supply its rated current no matter what is connected at the output. Meaning, if we rate the current source as 1 amp, it will supply 1 amp. It will change the voltage at its output terminals to match the requirement of the load, but 1 amp at the output terminals will remain constant. And that's what makes it a voltage source and a current source. And the way it functions on a real life device is there is a mode. There is a voltage, there is a constant voltage mode and a constant current mode. So on these devices, you will see CV and CC. CV and CC mode. So exact same device, but say constant voltage mode, CV mode, and this would be a constant current mode. So if you run the device in constant current mode, it becomes a current source. If you run it in constant voltage mode, it becomes a voltage source. A voltage source is going to supply current. A current source is going to supply voltage. Let's take a pause. Let me know if you have any questions before I move on to the example. Question? Okay. So far, so good. All right, let's take the example of a voltage source that is supposed to supply 10 volts. So a voltage source is rated for 10 volts. Let's say you connect a resistor of 1 ohm across the terminals of that 10 volt source. We all studied Ohm's law. We just looked at Ohm's law. V equals IR. V is 10, R is 1. What is my I? What is the current? I heard one answer say 10 amps. Right, exactly correct. Now, instead of 1 ohm, let's connect a 10 ohm resistor. What happens? Exactly, right? The voltage source is still going to supply 10 volts. It's going to keep it constant, but it changes the current to match the requirement of that load. So current now drops to 1 amp. And let's connect one more resistor, not one more, switch it out with a 100 ohm resistor. And current now drops to 0.1 amp. So again, it keeps 10 volts constant, but it now changes the current to match the requirement of the load. It goes to 0.1 amp. Make sense, right? And that's what makes it a constant voltage source or a voltage source in general. Now, of course, in real life, there are some other constraints. There are some other limits. So in the lab, if you're trying to do this, you don't want to blow things out, right? So there are current limits that we put in place. So tell me what happens to current if I was 0 ohm resistor between the terminals. Effectively, if we take a wire and short out our voltage supply, meaning connect the positive and negative terminals together, what do you think will happen? Well, V equals IR. Mathematically, what do you think I would be? Infinity, right? I would go to infinity. Right? I would go to infinity. So, two important things. We never, ever, ever want to short out the terminals of a power supply, right? Or a battery. Well, that's the reason why they say, do not put batteries in your pockets along with any other metal keys or coins or sharp, any metallic objects. You don't want to short out your battery terminals, right? Because no matter how small that voltage is, if R is equal to 0, current is always going to be infinite. And here are the real life implications. Few years ago, Samsung released the Galaxy Note 7. Anybody remember that phone? It came to be known as the exploding phone, right? What happened there was, in the pursuit of making smartphones thinner and thinner and thinner, some designers at the battery unit decided to make the walls between individual cells of the battery very, very thin. And so what happened was they inadvertently ended up shorting out the battery inside. Okay, so there are multiple cells inside a battery, and this battery pack goes inside the phone. So there's nothing that users can do, right? So that's just a design flaw. So the design in such a way that the walls were very thin led to short circuiting of the battery terminals. Now, a battery has some finite capacity. That capacity is huge. right? So when you short the terminals of a battery, what happens? All of the current or all of the energy that is stored inside that battery is released all at once. And what happens when electrical energy is transferred? What happens when you have a resistor? Dissipates as thermal energy, right? Electrical energy is converted into thermal energy, dissipates as heat. But there is no resistor in there. R is 0. Energy keeps releasing and releasing and releasing until the battery completely runs out. But before the battery can empty out, the thermal energy that is released has reached such high proportions that it becomes really, really hot and it explodes. And that was a real life example of what happened then. But again, that's the thing about resistors. Humble component, the most basic, most fundamental, the most important component of all. You can never ever build any kind of electric circuit without a resistor. As simple as that. Okay. All electric circuits, small, large, big, huge, doesn't really matter what kind of electrical system it is, they always need a resistor. Okay. The flashlights are different. Flashlights used filament light bulbs. Those filaments had their own resistance. Light was actually a byproduct of those filaments. Nowadays, we're hard pressed to find a filament light bulb, but if you've ever seen one, that filament actually glows, right? So it's a resistor, but it's inside a vacuum. It's a very thin filament. And so when it's dissipating as heat, a lot of the energy is also dissipated as light. So it gets hot as well as it has light. And that was the light bulbs. And now you have LEDs. LEDs, they say that they don't get as hot as light bulbs, but they still do generate heat. Okay, so primarily these are all LED lights. These LED lights, if you leave them running constantly, they're not going to get as hot as a filament light bulb. They still get hot. Okay, so LEDs also generate heat. Coming back to our concept here, current source is exactly the same. You run it in constant current mode. The same example applies. We take the example of, and I'll let you work through it yourselves. You can do it outside of class time. You have a 1 amp current source. And then you apply or connect resistors, the same 4 resistors. And then you calculate the voltage. And you can do that outside of class time. That's fine. V is equal to question mark. And it changes the voltage to match the requirement of the load. Now, there is a limit, obviously, right? You have a 10-volt source, and the 10-volt source can only supply some amount of current. It cannot supply 10 amps, not unless it's specifically designed, right? So you have these power supplies. There is a current limit setting that you will use every single time in the lab. Do not ever forget the current limit. Otherwise, your power supply is going to explode. And we don't want that, right? So if you connect a 100 ohm resistor and you have 10 volts applied, you have 0.1 amps. You connect a 10 volt source or 10 ohm resistor, you have 1 amp. And let's say your power supply can only supply a maximum of 1 amp, right? It can only supply, let's say its rating is only 1 amp. Now, if you connect a resistor of 1 ohm, it cannot supply 10 amps. You put a current limit on it so as to not blow it out. And so your power supply will go into circuit protection mode and it'll turn off. Okay. So there is a limit, and the limit is, entered in there for safety purposes. All right. So keep that in mind when you're doing the lab. All right. We're going to end class here today, and we'll pick up here again on Wednesday. We'll go a little bit faster than this, but this is like the first one, so I'm taking a little bit slow. All right.